Hello, everybody. Welcome to the Mathematics Mindset Academy, where maths actually makes sense. So, today in this video, I will be covering ring theory. So, I'll try to cover the definition and example. So, the example that is actually very important, and you will see that in your university exams, it always comes. So, let us begin with the definition. So starting with ring. So we need to know what exactly a ring is. So we take a non-empty set. Let us say it is some R, and we'll take it together with some binary operations, addition and multiplication. Let me first jot down. So what are these two binary operations? These are additive and multiplicative. Let us denote them as this sign, and for multiplication we denote it by this sign. So for a ring, it has to basically follow some postulates or some axioms. Not postulates, actually axioms. So is said to be a ring. Said to be a ring if it follows the following axioms. So I hope it is like clear. Yeah. So for the first, we'll be doing it with respect to addition. So there are few properties that we need to follow. So what are those? So the first one is the closure property. So we need to satisfy this closure property. So what we'll take any two elements. Let us say a comma b. We're taking it from the set R, and their addition, this b, must belong to this R. So it implies that it is closed under addition. Closed under addition. All right. So what is the next property? This is the associative one. So what we'll do, we'll take three elements. Say for example a, comma b, comma c belonging to this R. So what is the property that it needs to satisfy? It should follow this. Or vice versa, like a plus b plus c must be equals to a plus b plus c. So this, you can write it like this also, like this also. So we say that this property is satisfied. Now for the third property, this is called the existence of additive element. So what happens here is there exists an element. This element is this one, belonging to R, such that 0 plus a should be equals to a is equals to a plus 0. This is absolutely right. Why? Adding any number to 0 will give the same number only. So this is called the existence of identity. So this is existence of identity element. Now for the fourth property, what we say is that for every a belongs to R, for every this a element must belongs to this R, such that, not such that, there exists an element minus a belongs to R, such that it should be like this. Their addition should give 0. So this is called the existence of additive inverse. This is called existence of additive inverse. Now, for the fifth property, with respect to addition, it should be commutative. That is, a plus b must be equals to b plus a. So we say that commutative property holds here. Now, these 5 properties were of addition properties. Now for the multiplication. Now for the multiplication properties, I'll write it here only. So multiplication properties. What are they? So the first one, likewise of addition, that it should be closure. So A dot B belongs to R. So we say that closure property holds here. Now the second property, that is associative property. So that is A dot B dot C is equals to A dot B dot C. It must satisfy this particular thing. Then we will say that it is multiplicatively associative. That multiplication is associative. Now for it to be a ring, it should follow these 2 properties of multiplication. Now comes a very, very important property, that is distributive property. Distributive property. So for a ring, it must follow distributive laws. So what are those? That A dot B plus C must be equals to A dot B plus A dot C. Now second is A plus B dot C is equals to A dot C plus B dot C. So these are the distributive laws. So now we say it is a ring if it follows these 5 properties of addition and these 2 properties of multiplication, and it should follow the distributive laws. So the distributive laws goes like this. Now we can say that it is a ring. So it is a ring with binary operations, addition and multiplication. And denotion, I mean, how do we denote it? So the algebraic system is R plus dot. This is a ring. This is the algebraic notation. All right. Now, when do we say that R is commutative? So commutative ring. Now we'll talk about commutative ring. Commutative ring. When do we say that? So a ring R, ring R with this notation is said to be commutative, in which it follows, in which this AB is equals to some BA for all A comma B belongs to R. So we say that this is a commutative ring, otherwise we will say that it is not a commutative ring. Now we'll define what is ring with unity. What is a ring with unity? If it will have the identity element. So a ring we define as a ring R is said to be a ring with unity, is said to be a ring with unity if there exists, if there exists an element 1 belongs to R such that for all A belongs to R. So it should be A dot 1 equals to A equals to 1 dot A. So it is said to be a ring with unity. And now there are few examples. So in this particular video, I will be covering the most important one. Alright, so the example is that we are supposed to show that set of rational numbers Q is a ring under the composition this and this, addition and multiplication, which are defined as A plus B equals to A plus B minus 1. So, and similarly for A dot B, they have given this particular thing. So we are supposed to satisfy the properties of addition and multiplication, and we need to prove a ring. So how do we do this? So the first property, we know that it is a closure property. So what we'll do, we'll take two elements from the set of rationals. Then this A plus B minus 1 will also belongs to Q, and this implies that this is closed under the operation. So basically this plus with a circle around it and this multiplication with the circle around it, they're nothing but the only operations, and we have defined them likewise like this: A plus B minus 1 and A plus B minus AB. So we need to satisfy the properties as per these operations, right? So the first one we have proved that it is closed. Now for the associative one, we need three elements. So taking them from the set of rationals, likewise, then we need to operate this particular operation. So it will be like this, is it? Let us take these closed brackets here. So it is given that with A operating on this B will give this value. So can we write it like this? So when this particular thing will operate with this C, what will it give? It will give A plus B minus 1 plus C minus 1. Is it? So now opening the bracket, we'll get A plus B plus C minus 2. Okay, so this is the first video. So if you feel that it should be bilingual, so I'll keep it that way. I'm just using English so that, everybody could get this. If you want it bilingual, do make sure to tell me. Also, I'm a bit nervous today, so please bear with me. So second is that we have shown this property. Now can we show it like this? A plus B plus C. So what will it give? It will give B plus C minus 1, and with this it will give A plus B plus C minus 1. So opening the brackets, we will get C minus 2, A plus B plus C minus 2. The results are same. We can see that. So we can say that associative here holds. So we can see that the property of associative holds here. So we can say associative holds here. Associative property holds here. Now what is the third property? That is existence of identity. So moving to the next page, you can see how I've done it. Take a screenshot if you want to. Now moving to the third property, that is existence of element. So how do we do this? So for each A, for each A belongs to rationals, we want to show that there is E, that is identity element, that belongs to Q, such that, so if we apply this operation on this, it will give A only. A. So now applying the operation, the result will be A plus E minus 1, and here it will be E plus A minus 1. Now this 1 belongs to what? This rationals. So therefore we can write for all A belongs to Q, there is a identity E equals to 1 belongs to Q, such that A operating on this identity will give A only. Similarly, this. Now existence of identity holds here. Existence of identity holds here. So the fourth property is existence of inverse element. So what we'll say, that for each A belongs to Q, we are to show that there is an element B that belongs to rationals, such that if we apply this function on B, it will give the identity element, like this operation, not function. And so can we get A plus B minus 1 equals to 1 is equals to B plus A minus 1. So if we solve this, for example, A plus B equals to 2, that is B is equals to 2 minus A. This will belongs to rationals. So we can say for all A belongs to Q, there exists an inverse element. There is an inverse element B equals to 2 minus A, which also belongs to this rational, such that A is, or like A operating on this B will give 1, which is this only. So again we have proved this existence of inverse element, existence of inverse element. Now we'll show that commutative property also holds here. So again, taking two elements from rationals, and we know A operating on this B will give us A plus B minus 1. Why are we taking this? Because it is already defined in the question. So we are doing as per the question demand. So it is B plus A minus 1. It can be written. Why it can be written so? Because since AB belongs to rationals, this implies that their addition can be written like this, B plus A minus 1. So we can get that B operating on A. These are same results. So yes, commutative property holds here. Commutative property holds here. Now these all were the properties. These all 5 properties were with respect to addition. Now we are supposed to show properties of, we need to prove some properties of multiplication. All right. And this particular question, you can see it has came in 2018 HPU University exam. So and also in Punjab University. So yes, this is an important question. You can fetch like 5 or 7.5 marks out of this If it is of 7.5, you can get full. If it is of 5, you can get full. So please make sure that you do this question, this particular example. So for properties of multiplication, again, we need to show the closure property with respect to multiplication. A comma B belongs to Q. That is, and if you see what was given in the question, that for multiplication, so when this particular operation operates on AB, this will be the result, and that is A plus B minus AB. So now for this, that is properties of multiplication. So we can say that A plus B minus AB belongs to this rationals. How we can say that? Because these two elements belongs to rationals. That means their addition, their multiplication belongs to Q. That A plus B minus AB belongs to rationals. So this implies that A operating on this B belongs to Q. So yes, Q is closed under this particular operation. So next, we have proved this closure property. Now we are supposed to show the associative ones. So for the associative property, we need to take 3 elements like we did in addition part. So associative property. So we'll take 3 elements for all A comma B comma C. I hope it's visible to you. Belongs to Q. Now operating on this, what will this give? This will give B plus C minus BC, right? And now this A will operate on this particular thing. So what it will give? Now pay attention. This will give A plus B plus C minus BC, and then minus A B plus C minus BC. All right. Now A plus B plus C minus BC minus AB minus AC and plus ABC. So this is the result. Now if we apply this operation like this, what we'll get? We will get A plus B minus AB. Now operating with C will give A plus B minus AB plus C minus A plus B minus AB bracket C. So A plus B minus AB plus C minus AC minus BC plus ABC. So this goes like A plus B plus C minus AB minus AC minus BC plus ABC. So we can see this result and this result is equal. That means associative here holds. Not C is equals to A dot C. So associative property holds here. Now we'll show the distributive laws. So for each A, B, comma C belongs to Q, A, so it will be written like B plus C minus 1. This is basic maths. So that's why I'm not going deep into explanation part. This is like every math student, like postgraduate students and graduate students can do this. So it can be written like this by the definition. Plus B plus C minus 1. A plus B plus C minus 1 minus AB minus AC and then plus A. So this A and this A is 2A. This BC, write it like this, minus AB minus AC and minus 1. So now, sorry, this was plus A dot C. So this is what? A plus B minus AB operating with this is A plus C minus AC. Now operating in this, what will get? This will be A plus B minus AB plus A plus C minus AC minus of 1. So now if we see this A, 2A plus B minus AB plus C minus AC minus of 1. So 2A plus B plus C minus AB minus AC minus 1. So what do we see? That this is equals to this. That means these two are equal. Then that is this. Not applied this here. Yeah. C for all A, B, C belongs to Q. Now similarly we can show that this B operating on this addition, and this is equals to what? B dot A, C dot A. A for all A, B, C belongs to Q. With same process, you have to repeat the same process and you will get these two will also be equal. So yes, now we can say that hence Q is a ring with respect to the given operation. And I assure you, you will see this in your final exams, this particular example. So make sure that you do this, and we'll see each other in the next video. And please show me love. Please make sure to subscribe, like, and share this video. Share it with your friends so that it can help them as well. And so see you in the next video.